Welcome back, children, for the continuation of semiconductor electronic devices. So far, in the first video, we have seen about the importance of the semiconductor. How does it differ from ordinary vacuum tubes? And in order to control the flow of electrons, we require PN junction. So you know that semiconductor is made up of it is consists of two types. So one is pure semiconductor, that is called intrinsic semiconductor. What is an intrinsic semiconductor? Made up of materials, silicon and germanium. What is the valency of silicon? 4. Germanium is also 4. But then, though the valency of germanium and silicon is 4, the ionization energy is different, because the valence electron in the silicon is in the 3n state. What state? 3n state. So it is little closer to the nucleus, whereas valence electron in the germanium is in 4n state, little far away from the nucleus. Therefore, the ionization energy is different. For silicon, it is 1.1 electron volt. For germanium, it is 0.7 electron volt. But then both are used for making semiconductor electronic devices. So it is possible by means of an external agency or by means of an external support, external voltage or external electric field, you can control the flow of electron, you can make it to conduct. And we have already seen that the semiconductor at low temperature doesn't conduct, and the semiconductor, the energy gap, even though it is less than 3 electron volt, it is possible for conduction only at T greater than 0 Kelvin. At T is equal to 0 Kelvin, what's happening? We have no free electrons, hence we have no conduction. We have seen that, right? Now T is greater than 0 Kelvin, the covalent bond breaks. Due to that, the electrons are left free. When the electrons are left free, that is a vacancy created. What is that vacancy called, as children? That is an empty space. That is called as hole. Okay? What happened to the hole? Apparently moves. Keenly observe. The hole which is created here, the covalent bond is broken. It has pair, this has pair, this has pair, adjacent silicon atom as paired with electrons, whereas this alone do not have pair. So what does it do? It seeks another electron, therefore pulls out an electron here. Hence the green color line shows that attraction of electron from the neighboring covalent bond. So therefore this electron goes. Apparently there is a vacancy created. Earlier, where was the vacancy? In site 1. Now where is the vacancy? In site 2. So apparently the vacancy moves opposite to the direction of the electron. Hence you can say that one electron is creating one vacancy. Therefore the electrons and holes are responsible for conduction. So which is responsible for conduction? Electron as well as hole. Is the hole moving? Actually no. Apparent movement of the hole. Why apparently moving? Because the electrons are moving, hence therefore apparently the holes are moving here. The electrons and holes are responsible for conduction. So therefore for n electrons, n holes are produced. So therefore which is responsible for conduction in the semiconductor? Both electron as well as holes. Both electrons and holes both are equal in number. How this is being developed? It is developed only due to thermal agitation, but it is very less in number, only due to high temperature. So it is less in number, hence to increase the conductivity, what you are doing? Doping. So in order to increase the conductivity, so we do doping here. Yeah, so we will see that doping, how it has been done here. Yeah. we will show where is the doping. Yeah. Now we have to dope in order to increase the conductivity, and the pure semiconductor Ne is equal to NH is developed. So therefore it is not enough, because you have to increase the temperature, only less amount of electrons or the holes can be created. So therefore you have to add suitable impurities in order to increase the conductivity. So if you dope the semiconductor, is no longer called as intrinsic, this is called as extrinsic semiconductor here. And what are the characteristics of the dopants we have seen already, but once again I will just giving you a recap. It should be compatible to the size of silicon atom, and also it should not disturb the crystal structure, and it should increase the electrical conductivity. So all these three criteria has been met with only these two type of impurities. So what are the two types of impurities? The two types of impurities is N type as well as P type impurity. That is nothing but pentavalent impurity and trivalent impurity. When you add pentavalent impurity, that is phosphorus, arsenic, antimony, valency 5, you get N type semiconductor. And when you add trivalent impurity, that is aluminum, boron, indium over here, you get P type semiconductor. So let us see here how this N type semiconductor and P type semiconductor are produced. So now here we will check this N type semiconductor. Yeah, this is N type semiconductor. Sorry for the delay, children. Here I have taken the phosphorus atom. We know that the phosphorus atom has got 5 valence electron. So 1, 2, 3, 4 forms a covalent bond, whereas the 5th electron is left free and it is not been bonded with anyone. So therefore one phosphorus atom produces 1 free electron. Already we know that for the silicon atom which is present here, we have Ne is equal to NH is produced. That is only due to the temperature. But the temperature, with respect to the temperature sensitive electrons and holes are less in number. By when you add more amount of impurities, more and more amount of impurities, more number of the 5th electron will be left free. So in fact you can say that the number of electron is more than that of the number of holes already present, because more the number of electrons over here, the number of holes would have been keep on what? Reducing here. So therefore number of electrons is very much greater than that of the number of holes, because this number of electrons and holes due to thermal agitation formed by the silicon atom is less in number. You get it? Already for silicon Ne is equal to NH is produced. That is due to the temperature. That's there. But addition of impurities, when you add this phosphorus atom, you get excess number of electrons. So therefore these excess number of electrons prove that it is rich in electron. Hence this kind of semiconductor formed is called as N type semiconductor, whose majority charge carriers are electrons here. There also be rate of recombination taking place in the pure semiconductor. In note, in pure semiconductor, the rate of recombination is equal to rate of generation in pure semiconductor. So that means Ne is equal to NH is already present, right? So that is in pure semiconductor. So that pure semiconductor charges are already existing, Ne is equal to NH. But when you add some impurities, these electrons are excess, hence Ne greater than NH is produced. Since Ne is greater than NH is produced over here, so therefore you can say that the N type semiconductor has got excess number of electron. Hence the modified energy band diagram should be drawn in such a way that it has got enough energy to just move to the conduction band. So therefore this donor level has to be drawn over here. So why do we draw donor level here? The donor level, why do we draw here? Because it has already attained excess energy, and sufficient energy is little enough, an amount of energy is enough to just move to the conduction band, that is 0.01 electron volt. So therefore you can show here for silicon atom you have 4 electrons, valence electron, phosphorus 5 valence electron, so totally 9, plus 1 thermally generated electrons, so totally 10 electrons you have to show, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But see to that only 2 electrons you are drawing in each energy level according to Pauli's exclusion principle. What is this white in color? That is a hole generated due to the thermally generated electrons. This is thermally generated electron, that corresponding hole is preferably marked in white. Okay. Come back to this p-type semiconductor. So, p-type semiconductor is obtained by adding trivalent impurity. What is the valency of aluminum here? 3. So, therefore, you can say 3 electron form covalent bond with the adjacent silicon atom. But the formation of the fourth covalent bond, you need 1 electron, right? There is no electron at all. There is a deficiency of electron, that is called as hole. So, 1 aluminum atom produces 1 hole, n aluminum atom produces n holes. Therefore, majority charge carriers are going to be holes. And as we discussed earlier, E is equal to NH is already present. Addition of aluminum atom produces excess number of holes. So, therefore, you can say that NH is greater than Ne is produced. So, which is the majority charge carriers, children? Majority charge carriers are holes. So, now keep that in mind, and then you can say that P junction has got excess number of holes, and N junction has got excess number of electrons. N junction has got, N-type semiconductor has got excess number of electrons. Do you mean to say that there are no holes? No, you can't say that. So, there are certain holes. That is called as minority charge carriers. So, this is holes, minority charge. Here excess holes, but very minority charge carriers, electrons is less. Now, let us see, so far we have seen p-type semiconductor, n-type semiconductor. Now, you are going to see p-n junction formation. What junction formation, children? p-n junction formation. So, let us see that p-n junction formation. p-n junction formation. Listen very carefully. I am going to give you a gist about it. Short, sweet, crispy learning here. Okay, though it is a paragraph, if you know the content of it, you can elaborately write by yourself. p-n junction, first of all, you take a p-type slab. This is a p-type slab, children. This is n-type slab. Physically, if you join and then after that you say that, oh, the charges from n-type is moving to the p-type. You can't say like that, because physically there is no possibility for the charges to flow from p-type to n-type. Therefore, you cannot join. There will be a discontinuity in the flow of charges. You must have learnt about the interatomic spacing. So, there is a discontinuity in the flow of charges. Therefore, one p-type layer, p-type slab cannot join with the n-type slab, form a p-n junction in order to have the continuity in the flow of charges. When can you say that p-n junction is conducting? Only when the electrons move from one place to another, where you can say that only if the charges are moving from one place to another. Since it is not happening physically, you take a p-type semiconductor. After taking a p-type semiconductor, already we know that the p-type semiconductor has got excess holes, upon which the p-type semiconductor, so we are going to add impurities of n-type over here. Take p-type semiconductor, add impurities of n-type over here. So, in that what you have, due to p-type it has excess number of holes. Due to p-type it has excess number of holes. Do you mean to say that there are no electrons? No. It has electron, but it is less in number, that is minority charge carrier. Do you understand? But at the same time, if you take n-type, excess number of electrons are present. Do you mean to say that there are no holes? No, there are holes which is lesser in number. Now what is happening? There are two processes taking place. What I have taken, take P type, you have to take P type wafer. Wafer I am taking. Now add impurities of what? Add impurities of N type. Take P type and add impurities of N type. Got it? Now what you do, I have added impurities of N type. Number 3 point. After adding the impurities of N type over here, electrons from N side, slowly move to, it's all free electrons, right? N side move towards P side. Electron from N side move to P side. Okay, then what will happen? When the electrons moves over there, what will happen? These electrons are moving here. What will be created here? Yes, that is a vacancy which is created here. This electron go and sit over here. So what will happen? The vacancy is created over here. Electron from N side move towards P side and holes from P side move towards N side. So this transition keep on happening. Therefore, thereby creating a negative space charge region. Electrons gone over there, right? Negative space charge region. Near what side? Where negative space charge region? Here, near P side. Okay. Then positive space charge region, what side? Creating positive space charge region. Near N side. So near N side, a positive space charge region is created. So next page I will go here. So therefore you can say a negative space charge region is created near P side and a positive space charge region is created near N side. This becomes immobile. It is separated by some distance. So this is immobile and it is separated by some distance. Okay. So this means keep on creating over here. So these two constitute immobile ions, immobile charges, immobile ions constitute a region called as depletion region. What region, children? Depletion, very easy, children. N rich in electrons, P rich in holes. Electron from N side move toward the P side. So when all the electrons, that means most of the electron move from N to P, slowly the holes will come and occupy the position. So therefore this is called as immobile negative space charge region. Where is the negative space charge region created? Negative space charge region created near P side and positive space charge region. Where is it created? Created near N side. These two regions create an electric field. Can you see here? These two regions, you cannot get it nullified, whereas it is creating an electric field. Since it is creating an electric field, already what happened? There are minority charge carriers present at the P. Which is minority here? Minority is electrons. Here which is the major minority here? Here minority is holes. Minority charge carrier. Is it only one? There are few in number. This electric field which is created, right, pulls the electron. Pulls. When does it pull? Immediately when the electric field is created. So immediately pulls this electron from P side to N side and vice versa, and this is called drift. The electrons from n side move towards the p side, is there? No. This electron from n side move towards the p side, holes from p side move towards the n side. What is this process called as? This is called as diffusion. Listen very carefully, children. First process very easy, diffusion. How does p-n junction is formed? Just 2 points. Point number 1, diffusion. What is diffusion means? Movement of the majority charge carriers. Which is the majority charge carriers in p side? P side holes. Which is the majority charge carriers in n side? Electrons. So diffusion means movement of majority charge carriers. Majority charge carriers. That is movement. Electron from n side move towards the p side and holes from p side move towards the n side. That is diffusion. Due to diffusion, immediately an electric field is created. Electric field is created. The electric field created, that means due to the separation of the charges, due to the immobile charges, where negative space charge region near the p junction, positive space charge region near the n junction, creates an electric field. So electric field created, and hence drift takes place. Now only we saw what is drift takes place. Drift is due to movement of minority charge carriers. Minority charge carriers. Then what will happen? The diffusion takes place, drift takes place. Both are being done at the same time. So therefore the diffusion, due to diffusion current is produced. Diffusion current is produced, and due to drift current is produced, and the drift current is due to minority charge carriers, opposite to that of majority charge carriers. So therefore this all keep on extending till drift current and diffusion current are getting nullified, because it is equal and opposite to each other. So therefore one particular instant when diffusion current is equal to drift current, the net current will be equal to 0. Thus p-n junction is formed. So it's very easy to just remember, children, and also easy to understand as well. We have already seen what is p-type and what is n-type semiconductor, and what is responsible for current in the semiconductor, children, which is responsible for conduction. The holes as well as electrons. How can you get hole current and electron current? Only if you give external field. Already in semiconductor you have to give some external supply, therefore electrons and holes move each other and produces, but it is possible only at higher temperature. But it is not enough, therefore you add some impurities. When you add suitable impurities like pentavelent impurity, you get what type of semiconductor? N-type semiconductor. What type of semiconductor is obtained by adding pentavalent impurity? N-type semiconductor. The next, what type of semiconductor is obtained by adding trivalent impurity? P-type semiconductor. So p-type separately, n-type separately I have taken, and then I want this to join in order to make the charges to flow, because my aim is to control the flow of charges, whether the electrons or holes. So allow it to move, because conduction I want it, but it is not possible because physically there will be a discontinuity in the flow of charges. Hence what am I doing? I am taking a p-type semiconductor and impurities of n-type, and then after adding you can say both the charges are present. They try to move each other. So when they try to move each other, there is a negative space charge region is created near p side, positive space charge region is created near n side. These two charge immobile ions, you call it as depletion region or diffusion region. Barrier, it becomes a barrier. So that I haven't told you, I am going to tell you. This region you call it as depletion region. Negative space charge region and positive space charge region constitute a region called as depletion region. Now once the diffusion current is equal to drift current, net current becomes 0. So therefore no charges can flow from N to P, no charges can further flow from N to P or P to N, because this will repel. The electric field pulls it, no. So once becoming a barrier here, this becoming a barrier. Since it's becoming a barrier over here, there is a potential created because of the distance, because of the electric field. That potential created, you call it as potential barrier. Potential barrier, which is denoted by the symbol Vb. In order to overcome the potential barrier, you have to give a biasing. So hope you understand, children, what are the two processes taking place in the formation of the PN junction. In the formation of the PN junction, there are two processes taking place. One is diffusion, another is drift. So because of the diffusion and drift, and a space charge region or depletion region is created. It creates an electric field and produces a potential difference that is called as barrier potential. In order to overcome the barrier potential, you have to give a biasing. So let us see how biasing can be done here. Okay. So all this I have already. Now whatever we discussed only I am just talking about. So this is a space charge region. Negative space charge region is created, positive space charge region is created, and this thickness of the region is that is in micrometers. Here you could have seen here, due to positive space charge in N side and negative space charge in P side, electric field is directed from positive charge toward the negative charge. Due to this, electrons on P side of junction move towards the N side, hole on N side move towards the P side. The motion of the charge carriers due to electric field is called as drift. Thus, a drift current opposite in direction to the diffusion current starts. So we have seen all that. Now I am going to give a biasing. So now this is without biasing, no biasing here. It is under equilibrium. Since no biasing, diode is under equilibrium, barrier potential is no bias. So there is no possibility for the charges to move from N to P or P to N here. Okay, the net current becomes 0 under equilibrium. So now what happens? I am going to give a biasing. What do you mean by biasing? Biasing is nothing but connecting to a battery, children, nothing else. See, I am connecting to a battery because in order to make the charges to flow from N to P or P to N, because in the N side lot of electrons are present apart from few holes, apart from few electrons here. But when I give P to positive and N to negative, I am going to give P to positive, N to negative. Positive and positive, what does it do, children? Positive and positive, what does it do? This is positive, this is also positive, majority charge carriers. What does it do, positive and positive? Positive and positive, repel. Here similarly, negative and negative, repel. Due to very high repulsion, external electric field we are giving. Due to repulsion, what will happen to the depletion barrier or barrier potential, depletion region thickness? Thickness further reduces. Already we have seen that the thickness is this much. The space charge region is depletion region, and this region is too high. The thickness of the depletion region is 1/10 of the micrometer. 1/10 of micrometer. But that is also microscopically it is too high. So therefore, charges are not able to deplete. So therefore, what am I doing? I am trying to decrease the thickness. How? Give forward biasing. What do you mean by forward biasing? What do you mean by forward biasing? Forward biasing means you have to give P to positive, N to negative. That is all. This is P, this is N. P is connected to high potential, N is connected to low potential, that is called as forward biasing. This is forward biasing. Forward biasing. Hereafter, let me call this as FB. P is connected to positive, N is connected to negative. Already some electric field is present here because it is negative space charge region, positive space charge region, due to which electric field is present. Or you can say potential barrier is in this direction. But externally you are applying, no. Look at that potential direction, positive to negative, no. So look at that potential direction. That is opposite to barrier potential. So therefore, net potential what will happen? Reduces V minus VB. So net potential reduces. Since it is reducing net potential, potential barrier decreases. Barrier potential decreases. Barrier height decreases. Either you can say barrier potential decreases or you can say barrier height decreases. You see children, this is the original barrier. This is PN junction diode under forward bias. B, barrier potential without battery. See, one is without battery. One is without battery, very high barrier height. See, this is valency band, this is conduction band. Now, no biasing. No biasing means no voltage supplied. Now, I am going to supply a voltage. What voltage? Forward biasing. When I give forward biasing, the depletion region width reduces. Now, look at that width. Now, earlier it was like this much energy gap. Now, what happens? Due to forward biasing, energy gap reduces. Valency band and conduction band are close to each other. So, therefore, the electrons from valency band move to the conduction band and easily conduction is possible. Or you can say electron from N side move to the P side and conduction is highly possible. So, without battery is 1, low battery voltage is 2, high battery voltage is still more reduces. So, therefore, you can say due to applied voltage, due to what voltage? Applied voltage. Electron from N side cross the depletion region and reaches the P side. Similarly, holes from P side cross the depletion region reaches N side. This process is known as minority carrier injection. Why minority charge carrier injection? You may be wondering, electrons are majority charge carriers in the N side, holes are majority charge carriers in the P side, electron from N side move towards the P side. But once this electron move and get back to this P side, what will happen to the number of electrons here? These electrons come here, no? So, number of electrons, what happens? More. Number of electron is more means in P side electrons are minority charge carriers. Therefore, number of minority charge carriers increases. Since minority increases, therefore, this is called as minority carrier injection. What do you mean by minority charge carrier injection? They will ask you. What you should say? Very simple. During forward bias, that's very important key point. During forward bias, due to the applied voltage forward bias, I am giving an applied voltage forward bias. So, electrons from N side move towards the P side, holes from P side move towards the N side. So, thereby increasing the number of minority charge carriers, hence it is called as minority carrier injection. At the junction boundary on each side, minority carrier concentration increases compared to the location from the junction. See, compared to the far from the junction. So, number of minority charge carriers increases, hence called minority carrier injection. So, now here, due to this concentration gradient, the injected electrons on P side diffuse from the junction edge of P side to the other end of P side. Likewise, injected holes on N side diffuse from the junction edge of N side to the other end of N side. This motion of charge carriers on either side give rise to current. So, it is very simple. Due to this concentration gradient, so that means number of minority charge carriers increases. The injected electrons on the P side electrons are injected. P side diffuse from the junction edge of the P side to the other end of the P side. From the junction end to the other end it goes. Basically, the electrons move towards the P side and sit in the hole. So, it becomes neutral now. So, now P side conduction is possible. One end to the other end it has to move, right? Now, conduction is possible. Electrons from N side move towards the P side, holes from P side move towards the N side because depletion region width decreases. Easily it can jump. So, conduction is easily possible. Therefore, this current give rise to current. The total diode forward current is sum of whole diffusion current and conventional current due to the electron diffusion. That means the total current is due to, I total is due to I electron plus I hole. That is all it says. So, you can see here injected charge carriers, electrons are injected here, the holes are injected here. So hope you understand this. So now yeah, so forward bias is over. Next, in the forward bias, what is happening to the potential barrier? So we will write down the same thing. So just about the forward bias. So summary about the forward bias. So what do you mean by forward bias? You have to give, take P N junction, this is P, this is N. What is this called as? The center part, that is nothing but depletion region. Depletion region. What is present in depletion region, children? Immobile ions. Negative space charge region near what side? Near P side. That is what you have to write. What is present in the depletion? Negative space charge region near P side, positive space charge region near N side. These two regions constitute what? That's called depletion region. So it produces electric field over here and creates a potential difference between the two ends, and therefore it is called as barrier potential. So therefore it creates a potential difference and therefore it is called barrier potential. Now in order to overcome the barrier, in order to decrease the height, so this is valency band, conduction band. Now I am going to give an external supply voltage P to positive, N to negative, or P to high potential and N to low potential. When you give it like that, so what will happen? The potential barrier become reduced. So this becomes V minus VB. So V is the external voltage and VB is the barrier voltage. So reduces over here. So therefore the electrons from N side move towards the P side and the holes from P side move towards the N side and increases the number of minority charge carriers, and this process is called as minority charge carrier injection. So therefore in forward bias, what happened to the depletion region width? Depletion region width decreases. What happened to potential barrier, children? Potential barrier height. Potential barrier height decreases. Thus, does conduction possible? Yes, conduction is possible due to what charge carriers? Majority charge carriers. But when it is going to that N side, electron is going to the P side, the number of minority charge carrier injection, that process is only called minority charge carrier injection. But current conduction is only due to the majority charge carriers. Thus, conduction is possible. Conduction is highly possible. Highly possible due to majority charge carriers. Which is majority charge carriers in N side, electrons, P side, holes. Majority charge carrier. That is all, children, forward bias. Now let us go to the reverse bias. Under reverse bias. Now just opposite. You take a PN junction and this is the depletion region. Now negative space charge region, positive space charge region. This is under equilibrium, so no conduction here. In P side, which is the majority charge carriers, holes. In N side, which is the majority charge carriers, electrons. Once after the formation of the depletion region, there is no possibility for the charges to flow because of the barrier height. Now there are few electrons, that is minority charge carrier, there are few holes, that is minority charge carriers. Now I am going to connect it to the external supply, reverse bias. What bias? Reverse. P is connected to low potential, N is connected to higher potential. Ulta you give. When you give, what happens? Earlier we have seen, right? Positive to positive, negative to negative, what will happen? Ripple. This one we have seen here. Ripple. So due to repulsion here, what happens? It crosses the junction. Here also ripple, so it crosses the junction. But at the same time here, this is positive majority charge carriers. This positive and negative, what does it do? Attract. Similarly, this negative and positive attract. Due to attraction, what happens to the barrier still more increases. It is attracting, no. So the barrier height increases. So now what happens, this barrier height increases. Barrier, earlier it was thin, now what happens, it increases still more. If it is still more increasing, what happens here? Is there any possibility for charges that is present in the, is there any possibility for the charges that is present in the P side or the N side to cross the junction? No chance. There is no possibility for charges to cross the junction. But with very high on end of voltage, there is a possibility for minority charge carriers. Minority is negative ripple. This minority charge carriers, there is a possibility to give rise to current, but potential barrier keeps on increasing. Since the minority charge carriers are less in number, charge carriers are very less in number, that current is very less. You can see that even negligible here, very small when you compare to the majority charge carriers. So therefore the conduction is not possible. So barrier height, what is happening? Earlier the barrier height was like this. You can see here, earlier the barrier height was like that. This is valency band, this is conduction band. As because you give an external reverse bias, what happened to the barrier height? Still more increases. So still more increases, V plus VB. You see here, this is V. Already VB is here. In addition to that, external VB increases. External voltage increases the barrier. So V plus VB. So that is equal to V net. So therefore, in reverse bias, potential barrier keeps on increasing. Barrier height increases. So conduction due to majority charge carriers is not possible. The drift current is also there under forward bias, but it is negligible when compared to the current due to the injected carriers, which is usually in milliamps. So the diode in reverse current, this is called as diode. The PN junction, I haven't told you, now I am telling you, this PN junction is called as two terminal device, therefore it is called as diode. If it is three terminal device, triode, now it is diode. The diode reverse current is not very much dependent on the applied voltage. You may be wondering that if you increase the applied voltage, oh, the conduction is possible because its pulling power is more. No, it depends only on the number of minority charge carriers, number density of minority charge carriers. Since the number density is very less, so therefore the current due to the minority charge carriers is less. So even a small voltage is sufficient to sweep the minority charge carriers from one side of the junction to the other side of the junction. So therefore the current is not limited by the magnitude of the applied voltage, but is limited by the concentration of the minority charge carriers. I have told you, right? It is not dependent upon the applied voltage, not much dependent upon the applied voltage, depends only on the concentration of the minority charge carriers. So this will be asked definitely in 2 more questions. The current under reverse bias essentially voltage independent up to a critical reverse bias voltage. That is called as breakdown voltage. When V is equal to V breakdown, the diode reverse current increases sharply. I have already told you this potential barrier increases, but in spite of that, you wanted to pull the minority charge carriers electron, so therefore increasing the external voltage. When you increase the external voltage, you can't increase it beyond a limit because the barrier width keeps on decreasing. If it is keep on decreasing at one particular point, what will happen? It reaches the breakdown point. So up to a reverse bias voltage known as breakdown voltage. When the V external is equal to V breakdown, the diode reverse current increases sharply. Even a slight increase in the bias voltage causes a large change in the current, because that voltage is enough to pull out all the electrons from the PN junction, that is N type, from the P side of the junction, because which is a minority charge carrier in P side, electrons. So, if the reverse current is not limited by the external circuit below the rated value, the PN junction will get destroyed. So, there will be a limit up to which you can just increase the reverse bias voltage. So, always restricted to increase. Beyond that, you cannot increase. If you increase, it will break. So, therefore, the manufacturer, while they are making, they keep that in mind. You will not be able to increase beyond that certain critical voltage. Once it exceeds the rated value, the diode gets destroyed due to overheating. This can happen even for the diode under forward bias. The forward bias current exceeds the rated value. And VA characteristics of the diode: forward bias, battery positive to diode, symbol of diode. Let me give you symbol of diode. Two terminal device, this is the symbol of diode. How your symbol of resistor you draw? Same way, this is the symbol. PN junction is there, no, that is called as diode, because P one junction, N another junction, so two junction. Since it is a two junction device, two terminal device, therefore it is a diode. And the triangle is positive, the linear line is negative. And if you give forward bias, positive to positive, negative to negative. But while you're writing, you should not say positive to positive, negative to negative. You should say P end to higher potential and N end to lower potential. Suppose, for example, if I give like this is what type of biasing is that? You check here. I am going to give 10 voltage here, and I am going to give 2 voltage here. So, 10 voltage is higher voltage, therefore it is forward bias. Suppose if I give minus 10 voltage and minus 2 voltage, then you can say which is more negative, minus 10. So, this is low voltage, this is high voltage, therefore it is reverse bias. You get it? That is how we need to find out. If I give this is 10 voltage and this is 2 voltage, then you can say forward bias. If I give minus 10 voltage, minus 2 voltage, then it is reverse bias. Hope you understand. So, positive to positive it has been given, and negative to negative it is given by means of my milliammeter, and take two wires from the voltmeter and connect it across. So, in order to measure, this is positive, negative, here also positive, negative, this is also positive, negative, and here this is negative, so therefore it is negative, positive. Similarly, reverse bias. The reverse bias change the battery polarity, that is it. Negative positive, here also negative positive. Battery positive is connected to diode negative. Battery negative is connected to battery diode positive, that is all. So, that is how you need to understand. So, if you want, I will just show you here diode positive negative. You connect it to battery positive negative, then it is called as forward bias. If you want to find out the current, how much it is flowing, always see to that the milliammeter should be connected in series. So, therefore, this is negative, this is positive, the milliammeter, and voltmeter should be connected in parallel to it, positive, negative. This is called forward bias. If you want to draw reverse bias, I am keeping it like that, diode positive, negative, keep it like that, or otherwise what you do, either you can change it, positive, negative, and reverse this polarity of the battery. See here, positive, P is connected to negative, N is connected to positive. And microammeter, because I have told you reverse bias current is not limited by the applied voltage, depends upon the concentration. So, microamps, this is positive, negative. Here it is voltmeter, negative, positive, that is it. So, and you can see the graph, forward bias, the current rapidly increases. This is called as cut-in voltage. The voltage at which the current enormously increases. You can see smaller voltage is enough to increase. So, enormously increases, that is called as forward bias or cut-in voltage. The reverse bias current is very, very small. Since it is very small, so therefore, you can say applied voltage is independent. You can see that applied voltage. Can you see that applied voltage very, very less. So, now current at one particular voltage enormously increases here. So therefore you can say reverse bias is independent of the applied voltage, depends only on the concentration gradient. So you must note down the threshold voltage or cut-in voltage. What is cut-in voltage here or threshold voltage? Voltage at which the current start increasing rapidly in the forward bias, that is called as threshold voltage. This is called as threshold voltage. Note down, children. Threshold voltage will happen only in forward bias. Okay, reverse bias you can see very minute change in the voltage, and at this breakdown voltage there is an enormous current. Beyond that, if you are going to increase the voltage, what will happen? It breaks. So heated up. It may also happen in forward bias. Okay, but then forward bias and reverse bias, what is the difference? Reverse bias, the barrier width increases, but forward bias, barrier width decreases, that's all. So now here the cut-in voltage for threshold voltage is 0.2 voltage for germanium and 0.7 voltage for silicon diode. You have to note down that. And we have already seen that reverse bias current is very small and almost remain constant with the change in bias. It is called reverse saturation current. And above discussion shows that the PN junction diode primarily allows the flow of current only in one direction. So therefore you can say that PN junction diode conducts only in forward bias. Conducts only in forward bias. Forward bias. You may be asking, reverse bias, it is very slow, very small, negligible. You can see the reverse bias current, that is in microamps, and that is very negligible. So here till this we won't go till this. Till breakdown we won't go. We will go just below the breakdown. So just below the breakdown you see the conduction current, not even 10 microamps. You can notice it here. So we will be restricting only till just before breakdown. We won't go till breakdown. So therefore just before breakdown you can't see any current. Therefore you can conclude that the diode does not conduct in reverse bias, conducts only in forward bias. No conduction in reverse bias. No conduction in reverse bias. That is the conclusion, children. So what is the conclusion drawn in diode? Diode, two terminal device, one is P, another is N. Triangle is P and straight line is N. When you connect forward bias P to positive, N to negative, that is potential barrier width or potential depletion region with thickness reduces, and current conduction is possible due to what charge carriers? Majority charge carriers. But in the case of reverse bias, barrier width keeps on increasing, potential barrier height increases. Since it is increasing, what happened? There is no conduction possibility due to majority charge carriers. That's what we have seen. But majority charge carriers does not conduct. But there is a possibility, least possibility for minority charge carriers under special condition by giving external voltage more. But even though you give external voltage more, even though you try to pull out the electron from P side to N side, the amount of current is not determined by the external voltage. It depends only on the number of minority charge carrier or minority charge carrier concentration. Since it is very less and almost the current is negligible. If you are going to increase the voltage till breakdown voltage, what happens? The junction breaks. So therefore it is advised, that means it has been restricted, the manufacturer restricted to use it just before breakdown voltage. When you break down voltage just before, if you are going to use, almost negligible current it flows. Therefore you can conclude that in reverse bias no conduction, forward bias diode conducts. So keep that in mind here. Therefore you can take in one example the reverse bias current. You can see here 1 microamps and 10 voltage is the reverse voltage. So if you want to find out the reverse bias resistance, you can say all the time you are getting same resistance R is equal to voltage, change in voltage by resistance R is equal to reverse bias resistance is equal to delta V divided by delta I. But is there any change in the voltage? No change in the voltage, almost zero. So therefore infinite. So here you can see from the curve V is equal to minus 10, I is equal to minus 1 microamps. So, but then here in the forward bias, when you see, there is a change in the voltage. So, resistance forward bias R is equal to, or dynamic is equal to delta V divided by delta I. So, you can see here delta V is nothing but this is 0.1 voltage and delta I is 10 milliamps. So, delta I is equal to 10 milliamps, 10 to 20. So, therefore, we will get 10 milliamps. So, therefore, 10 ohms is the dynamic resistance for the forward bias. Whereas, you can say that infinite resistance, because therefore, there is no change in the voltage, therefore, you can say that it is infinite resistance here. Okay. So, change in the current is equal to 0. So, 1 by 0 is equal to 0 to 10 voltage. So, therefore, infinite resistance you can say. Or if you want to typically find out 10 by 1 is that is equal to microamps, 10 power 6. If you say at 10 voltage, 1 microamps. So, resistance R is equal to V by 8, 10 by 1 into 10 power minus 6. So, therefore, 10 into 10 power 6. It is a huge resistance when you compare with the 10 ohms. You can even say that it is infinite resistance. Now, application of PN junction diode as a rectifier. So, you will see what is rectifier, application of PN junction. Rectifier is a device which converts AC to DC, alternating current to direct current. What is alternating current? This is only alternating current. This alternating current I am going to bring it as a direct current, smooth DC output I have to get. So, in order to get a smooth DC output, I am going to use a device called as PN junction diode. If you use PN junction diode, you can get the same thing. So, let us see how it is going to be used. So, what is rectifier, children? Now, only I have told you, once again let me repeat it. Rectifier is a device used to convert alternating current to smooth DC output. Alternating current to smooth, it is a fluctuating current, right? Smooth DC output. So, let us see how the rectifier works. So, there are two types of rectifier. One is half wave rectifier. Half wave rectifier. What does it use? Half wave rectifier uses only one diode. AC source, I am taking AC source. So, I have taken input is AC. I am using a transformer here. I am going to use a transformer and this is AC source. I am using a step down transformer connecting to a diode. Listen carefully the circuit diagram. You understand. So, I am using a transformer. Why do you use a transformer? Just to step down the voltage, because diode cannot withstand that much voltage. Very simple voltage, very less voltage is enough. So, this diode, this is PN. When does the diode conduct, children? Diodes conducts only in what bias? Conducts only in forward bias. So, the diode PN is going to conduct in forward bias. So, therefore, here I am going to find out take the output here. So, how am I going to take the output? You check here. So, there is a resistor I am going to use. So, this is called as load resistor. Load, whatever you are connecting, that is called as load resistor. Whatever you are connecting, that is called as load resistor. If I am going to connect a mobile, that is called as load resistor. So, this is input is AC. This is called as positive half cycle and this is called as negative half cycle. So, during this positive half cycle, the end A is going to be higher potential. How do you say higher potential? This is positive half cycle, right? Positive half cycle. So, end A is higher potential and B end is lower potential. You can say low potential. This is high potential. So, since it is high potential, can you say that the diode conducts a what? Tell me when does the diode conduct? We have seen no here. When does the diode conducts? We have seen here. When is it conducting? Conducting only when P is connected to what potential? Higher potential. And N is connected to what potential? Lower potential. So, same way here I am taking P is connected to higher potential and N is connected to low potential. Why higher? Because this is positive peak. Positive peak is plus 220 and this is minus 220, like that. This is plus 220. This is minus 220 voltage. So A is at higher potential, B is at lower potential. So therefore diode conducts. Current flows. See, current flows like that. Diode conducts. So therefore during the positive half cycle of input AC, so during the positive half cycle of input AC, I am taking. So during the positive half cycle of input AC, the diode conducts. So you get an output like that. Now what happened to the negative half cycle? So I am taking the negative half cycle. During positive half cycle it conducts. Now ulta, during negative half cycle, during positive half cycle of input AC, diode conducts. Why diode conducts? It is forward bias. It is forward bias. So therefore it conducts, since it is forward bias. Hence current flows. Now tell me children, what is happening to the negative half cycle? What will happen? Can you predict and guess? During negative half cycle of input AC, what happened? This is the negative half cycle, and A becomes lower potential and B becomes higher potential. Just ulta. I am taking this negative half cycle. So during the negative half cycle, and A is at negative potential, that is low potential. B is at positive potential, that is nothing but high potential. Now you tell me, does it conduct? It is what bias? Reverse bias. So diode does not conduct. Diode does not conduct, since it is reverse bias. Since it is reverse bias, does not conduct, no current flows. You have seen, no. Don't ask for the reverse bias current, because reverse bias current is very, very negligible and it is not depends upon the applied voltage as well, and it depends upon the concentration gradient. So it is very less. So therefore no current flows. We have seen that. So no current flows. So diode, what is the characteristic property of the diode? One and only characteristic property, it conducts only in forward bias, does not conduct in reverse bias. Keep that in mind. We have already seen that. Conducts only in forward bias, no conduction in reverse bias diodes. That property only we are looking at. So no conduction, so therefore you get a blank output. So you get a blank output, blank. Again what will happen, this process continues for the positive half cycle, it conducts, and then again it get a blank output. Again positive half cycle it conducts and it get a blank output. So like that what happens, you can see the output as well as the input. Input and output, right? Input and output. Is it continuous? No. So what is the conclusion of this? Conclusion is output is discontinuous, fluctuating, not only discontinuous, fluctuating, but it is unidirectional, fluctuating, unidirectional. Output is discontinuous, fluctuating, unidirectional. Now you check frequency. I am going to check here how much waves are present. Can you check the waves, number of waves? Here it is 1 wave, 2 wave, 3 wave. So frequency is 3. So 3 waves are there. See, one crest and trough is 1 wave, one crest and trough is another wave, one crest and trough is another. So how many waves here? Can have 3 waves. So therefore frequency is equal to 3. So the first one has got 3 waves, frequency is 3. What about the second one? How many waves are there? 1 wave, 2 wave, 3 wave. So therefore output frequency is also equal to 3. So, therefore, you can say output frequency and input frequency both are the same. Hence, I am going to write output frequency is equal to input frequency. That is all the conclusion, children. So, half wave rectifier is over. Hope you understand this. The next one we are going to go for the full wave rectifier. Full wave rectifier. Half wave rectifier, you are getting discontinuous DC output, hence I am going for full wave rectifier. Full wave rectifier uses two diodes and a center tapped transformer. So, two diodes I am going to use. Full wave rectifier, two diodes. Use that. So, now this is again AC input, AC input AC. I am using a transformer in order to step down the voltage. Now, here I am going to use a center tapped transformer. What tap transformer? Center tap. From the center you have to take and connect it to the earth. That is called a center tapped transformer. Listen carefully, children. Center tapped transformer. Now, this is positive, the diode. This is diode D1. There we used only one diode. Now, here we are using two diodes, D2. Now, directly I am not connecting to the load resistor. Instead, I am going to connect the two wires. Commonly, I am connecting it. And from here, I am going to take a load resistor, that is my output. I am going to connect it here to the center tapped wire. When I connect it here, here only I am going to take the output. So, I am taking the output here. If you keenly observe this is end A is higher potential, the end A, and this is end B. This is standard. Standardly I am maintaining 0 potential over here. Okay. So, now during the positive half cycle, end A is at higher potential with respect to O, with respect to the center tap transformer, with respect to C you write, with respect to C. End A is at higher potential with respect to C, hence it is forward bias. Which is forward bias? It means what? D1. Hence D1 is forward bias. And what about D2? B is at low potential. See, at the same time it is happening, same time. So, B is at low potential. This is minus, this is positive. Because low potential, minus 220, there it is plus 220, like that. Low potential with respect to C. Hence, D2 is reverse bias. So, hence, and no conduction. Reverse bias, no conduction. Whereas forward bias, conduction due to majority charge carriers. So, this will conduct. During positive half cycle, it will conduct. So, therefore, I will draw, this is 1, 2, 3. So, now during positive half cycle, diode D1 will conduct. So, hence output is uptime. So, during negative half cycle, number 2, during negative half cycle, end A is at low potential. Now reversed, during negative half cycle, end A is at low potential, B is at high potential. Low potential. Hence low potential with respect to what? With respect to C, and hence reverse bias. And end B is at high potential. B is at high potential with respect to C, and hence forward bias. Reverse bias, no conduction. Reverse bias. So, therefore, D1 does not conduct. Whereas here D2 conducts. So at the same time, both D1 and D2 are conducting in forward bias as well as reverse bias. So therefore, you get an output due to D2. Due to D1 it conducts, due to D2 it conducts, due to D1 it conducts. So therefore, you can say in both the cases, you can say here output and input. So this is output, this is input. So you get a continuous, fluctuating, but still it is fluctuating, unidirectional output. It is bidirectional, see here it is bidirectional. So therefore, but here you get unidirectional output. Unidirectional output, unidirectional means DC output, but it is fluctuating. And look at the frequency count now. So this is 1, 2, 3, 1, 2, 3, 4, 5, one more. This is 6. So D1, this is D2, this is D1, this is D2, this is D1, this is D2. So therefore, input frequency is equal to 3 over here, whereas when you take output frequency, how much you get? 6 over here. So therefore, what do you conclude? Output frequency is equal to 2 times input frequency. Whereas in the previous case, what did it do? Output frequency is same as that of input frequency, but here this result is different from the previous one. The last one, now in order to get smooth DC output, want to get smooth DC output, use filter circuit. So I am using filter circuit. So how am I using filter circuit? This is the output I am getting, 1, 2, 3, 4 like that. So this is fluctuating DC output. Now I am using a capacitor in parallel to that of the output resistor. If I use a capacitor, what will happen? The capacitor blocks DC. Since it is blocking DC over here, the fluctuating DC component, it allows AC, blocks DC, allows AC to charge, varying current to charge the capacitor, allows AC to charge the capacitor. AC is nothing but fluctuating current. So when it is allowing AC to charge the capacitor, once after charging, what will happen? It does not allow the DC current, hence DC will be dropped across it and you will get a smooth DC output. Since it is getting smooth DC output over here, so therefore you can say here this is called as filter circuit. Because filtering out the DC component and then you get a smooth DC output. Therefore, the voltage drop across this, the rate of fall of voltage across the resistor is equal to the dV by dt is inversely proportional to that of R and C. R and C value. In order to have the time constant is called as RC, where RC is equal to time constant, where RC is called as time constant here, time constant. In order to have a smooth DC output for the longer time, see here this part is there, no, so do not get confused. Here I have to get a smooth DC output. So in order to get a smooth DC output, I am using a capacitor. What does it capacitor do? The fluctuating voltage is there now, fluctuating, that means variation in the voltage. If there is a variation in the voltage, there is a variation in the current, right? We have seen now in EM waves. While you are charging, the capacitor, while it is charging, it conducts, that means it allows. But if it is completely charged, capacitor blocks, because Xc is equal to 1 by C omega. omega dc is equal to 0. So, therefore, xc is equal to infinity, right. So, complete dc blocks. Blocks means arrest, that means does not allow it to flow. It resists. If it is not allowing it to flow, then it has to drop out. That is a voltage drop. So, it only allows the fluctuating voltage or fluctuating current to pass through. But then the DC is there, no, the non-fluctuating constant one. It has a mix of both. Non-fluctuating, the constant one is there, no, that will be dropped across it. Therefore, you get a smooth DC output. Okay. So, whenever you have a fluctuation, that will be taken for charging it. Once after charging it fully, what will happen? The DC does not allow. So, therefore, whatever is not allowed, that will be dropped as the output. So, that is dropping as the output. But I want this for a longer time. In order to have it for a longer time, RC is equal to T, no. So, in order to increase the time of getting this DC output, I have to increase the value of C. So, C has to be large. So, I have the value of C should be large. C should be large. If you take the large value of C, the time constant is large. So, therefore, the voltage drop across the resistor is directly proportional to 1 by RC. So, this is how we need to get a rectified output voltage. This is called as rectified output voltage. So, hope you understand, children, the applications of both, the application of PN junction diode, that is half wave rectifier and full wave rectifier. I am just showing the NCERT book. Yeah, this is a transformer. Here you have an input, center tap transformer. This is a full wave rectifier, and A and B, and output here, waveform of A, waveform of B, because negative half cycle they have showed here, but I am not showed. So, this is positive half cycle, negative half cycle, but both the half cycle you get an output here. So, hence you can say output frequency and input frequency. Output frequency is double the times of input frequency. New output is equal to 2 times new input. But in the case of the fluctuating AC, I wanted to get DC component, use filter circuit. What is filter circuit comprised of? C and R. So, you get a smooth DC output. So, in order to make the time constant, large value of C should be large. So, capacitor input filters use large capacitor. Yeah, this type of filter is mostly used in power supplies. You can make a note of it. So, hope you understand this. And then this is forward, half wave rectifier. We have already discussed this. This half wave rectifier uses only one diode. This is discontinuous fluctuating DC. So, in order to improvise, we are using the full wave rectifier. Hope you understand this, children. And if you have any doubt, you can always reach me. I will just help you out. And here there is one problem based on, yeah, so suppose pure silicon crystal, we know that number of intrinsic charge carriers is number of electrons and holes, that is equal to Ni. Therefore, Ne into Nh can be called as Ni square. Ni is nothing but number density of intrinsic charge carriers. Number density of intrinsic charge carriers. Pure semiconductor. So, therefore, suppose pure silicon crystal has 5 into 10 power 28 atom per meter cube. So, Ni is equal to 5 into 10 power 28 per meter cube. 1 parts per million concentration of pentavalent arsenic. So, 1 parts per million is nothing but 10 power 6. So, 10 power 6 atoms. Pentavalent arsenic. Pentavalent means rich in what? Pentavalent is N-type semiconductor you get. N-type semiconductor you get. Calculate the number of electrons and holes. So, Ne into Nh is equal to Ni square. So, you can number of donor atoms you can take it from here. This is 5 into 10 power 28. So once again, let me just take the NCERT textbook for a minute. Yeah, so now you can say that the thermally generated electron, pure silicon crystal, is given 5 into 10 power 28, doped by 1 parts per million. Yeah. And pentavalent impurity means, I have already told you, rich in electrons. Calculate the number of electrons and holes. Here, the thermally generated electrons is approximately 10 power 6 per meter cube, or negligibly small as compared to those produced by doping. So therefore, the number of electrons is approximately equal to number of donor atoms. Therefore, I am taking Ne into NH is equal to Ni square over here. Therefore, NH is equal to Ni square divided by Ne. What is Ni square over here? 1.5 into 10 power 16 into 1.5 into 10 power 16 divided by this number of electrons, that is 5 into 1 parts per million, we have already done. 5 into 28, 10 power 28 atoms per meter cube. 1 parts per million, so that is nothing but 5 into 10 power 28 divided by 10 power 6. When it goes up, 5 into 10 power 28 into 10 power minus 6. So that is equal to 5 into 10 power 22. So it is doped with 1 parts per million concentration of pentavalent. Pure silicon crystal is doped with. If you take pentavalent impurity and then you are doping with the silicon, the number of electrons is going to be more. The number of electrons is going to be more, but number of thermally generated electrons, Ne into NH, is approximately neglected. That is what is given. So now therefore 1 parts per million, right, for per meter cube is 5 into 10 power 28. So therefore for 10 power 6, we are finding out. So therefore 5 into 10 power 22. So therefore number of electron is 5 into 10 power 22. So when you divide, you get approximately 4.5 into 10 power 9 per meter cube. So hope you understand this, children. And if you have still this kind of problems alone, you will be getting it. So once again, we will take number of electron is equal to the number of donor atoms. The number of donor atoms is obtained by adding this pentavalent impurity, and we have already given pure silicon is 5 into 10 power 28. We are adding 1 parts per million, and therefore it is 1 parts per million is nothing but for 10 power 6 only 1 part. Therefore for 5 into 10 power 28, how much parts? So 5 into 10 power 28 divided by 10 power 6. So 5 into 10 power 22 atoms, and that is number of electrons. By knowing this formula, you can find out the same thing. And thank you, children. This lesson is very, very important. You have to learn line by line from the entire textbook, and lot of insightful questions you will be getting it. And after watching the video, if you have any doubt, always reach me out. Thank you, children, and we will meet in the next video.